Okay, this is a little bit trickier. Level 3, number 5. This is the one where you have a rock sitting on a spring. And there's my rock. Now, when the rock is sitting on the spring, obviously the weight of the rock has compressed the spring 10 centimeters, 0.1. Let's make sure we get the conversion right there. 0.1 meters. Okay, so this is the initial conditions, right? And this is going to tell us some things. If we set up a description of this, let's do a force diagram, a free body diagram on this rock to see what kind of initial conditions we have. Well, there are two forces, right? There is a spring force pushing the rock up, which is counteracted by a gravity force pulling the rock down. So, if we did an F net equation in the y direction, we could put those two together. And since gravity is mg, and this force of a spring is kx, right? Then because the rock is not moving, there's no acceleration, then what's going to pop out of here, of course, is a k value. Everything else is known. So what you're going to get here is a value of k when you're finished. That value of k is going to be quite useful in the next part of the question, which is figuring out what happens if you push it down further. Okay, so let's push it down a little further. Here's the rock now pushed down further. It says push down an additional 30 centimeters. So that means that the entire compression of this spring is now 30 plus the 10 from before. So it's a 40 centimeter x value, right? The spring is compressed now 40 centimeters. And then what you're going to do is you're going to let go and see what happens. Okay, so here we have to think about how much energy is there in the spring now that it's been compressed. So 1/2 kx squared will tell us something about how much energy is in the spring. Once we know how much energy is in the spring, we know what's going to happen to that energy. The first thing that's going to happen is that, I wrote EK there, my mistake. I better erase that. That's spring energy. I wrote the right equation, but the wrong letter. Spring energy, right? But as soon as the rock springs up, it's going to leave the spring behind, and it's going to have right away a very large amount of kinetic energy. But that kinetic energy we don't need to calculate, because that kinetic energy then is going to change as the rock goes up in the air and slows down to a stop. It's going to turn into gravitational energy. So at the highest point, we have all gravitational. So the kinetic energy is like a transition energy. It's there, but really what happens is all of the spring energy that we started with up here. Oh, I meant to change colors there. All of this spring energy that we started with becomes the gravitational energy at the end of the scenario. So we don't have to worry about the EK at all. We can set this up as the energy before, energy after. I'm skipping, or total 1, total 2. And with these two equations, the mgh here and the spring energy there, we can jump right in. And we can figure out then, I think what it wants to know is how high it's going to go. So this is going to allow us to plug in our information and solve for an h. That should pop out in a nice happy number for you. Okay? So the trick to this question, we're trying to learn here, is how one form of energy is transferred into other forms of energy. But all that really matters is the initial starting point and the ending point. You don't have to calculate each individual transformation, right? At least not in this scenario anyway, in simple scenarios like these. And there's no waste. We're assuming there's no waste energy that's coming off of this. Like if there was, in reality, there would be some waste energy, and this EG would not be 100% the same as the spring energy.